Okay, hello everyone. Thanks to be there. Thanks for the students. Thanks people in the room. Thanks people online. So we start for the first session and we'll have two talks. So the first one will be given by two speakers physically. And I will talk about how to hack a TV, a smart TV. Is it smart enough? We'll see with the talk of the two speakers. And after we'll have a second session with a remote talk because person cannot come here due to COVID problems. So we'll have the chance to have the two physical person who will give us the first talk. So please, the floor is yours.
Et moi, est-ce qu'on m'entend?
C'est bon?
Non. Moi non plus. Ah.
Toi parle.
Et moi, si je parle, on m'entend? Non. Petit problème de micro.
The GreHack talk with second mic. So who will start to speak? Should start here. Give me the mic, and you can start to talk. Fair enough? Can you speak? Try to speak there.
Hello. Can you hear me?
Yeah. Okay, so this is a practical security. Let's go.
C'est bon?
Yeah.
Okay, so let's go for our talk. So we are Vincent and Jérémie from Synactive. We are security researcher at Synactive. Synactive is an offensive security company based in France. We have Paris, Rennes, Toulouse, and Lyon. We are almost 90 people, and we are hiring, so you can contact us if you want.
Try again.
Okay. Is it working? Yeah? Okay. Okay, so today we are going to talk about the Samsung Q60T Smart TV. So it's a device connected to internet. It has many network services. Sorry. And it's based on Tizen OS. So why did we look at this target? Because last year it was a .1 target with $20,000 reward. It has been targeted multiple times at .1. And when you want to search for vulnerabilities in this smart TV, you have a problem, which is that the firmware is encrypted, and you cannot find any decrypted version on the internet. So you have to find an entry point to start doing reverse engineering or vulnerability research. So the OS is Tizen. It's an open source multi-platform operating system based on Linux. It's maintained by Samsung. It's used on smartphones, smart TV, watches, and you can find three types of application. You have web application, .NET application, or native application. And of course, it uses a web browser, which will be our entry point. So the attack plan and the summary of our talk, we will start with the web browser, which is the entry point to get a shell on the device. Then we will have a privilege escalation by auditing some open source code and exploiting the kernel. And last, we will find the firmware encryption key in order to be able to decrypt the firmware offline. So Jérémie will start by explaining how we explore the web browser.
Thank you, Vincent. So, as said, our entry point is a web browser. So, depending on the TV model, the web browser could be based on Chromium or WebKit. So, in our case, this is a Chromium-based browser. The source code is available online on this Git repository. So you have all the patches which Samsung has added to the browser, and this is based on an old version. So it means that security patches must be backport by Samsung manually. So this is not an easy process. Maintainers must be very attentive and quick, and some commits are not marked as security fixes. So you must be there is a lot of vulnerabilities that is not patched by Samsung. So we found one vulnerability which is not backported by Samsung, and unfortunately this is not a valid entry for 0.1 because this is an already known vulnerability. But this is still interesting for debugging purpose because we can have a shell on the TV and do what we want. So the vulnerabilities that we found is on the JavaScript engine and on the JIT compiler. So the V8 is a JavaScript engine of Chromium. And a JavaScript engine is made of multiple components, such as the parser, which takes JavaScript and parse it. You have the interpreter, which compile and execute the parsed JavaScript into virtual machine code. So every JavaScript engine has its own virtual machine. And you have the JIT compiler, which takes the virtual machine code and compiles it in native instructions. So in x86 or ARM, depending on the platform in which the browser is executed. So while the JIT compiler is compiling, it tries to do optimization based on assumption, such as the range of variables, the types, and so on. So here you have the interpreter, which takes the JavaScript and execute it. So the compilation is very fast, but the code execution is pretty slow. But and when the code is a function is executed a lot of time, the JIT compiler takes it and compile it in native instruction. So here the compilation is pretty slow, but the code execution is more fast. And when there is a problem in the JIT code, on assumption, for example, the JIT bail out on the interpreter. So the vulnerability we exploited is a CVE from 2020, which has not been backported by Samsung, and it's a bypass of an older CVE from 2019. This is a type inference problem in the manner of V8 handle JavaScript loops, and in the Chromium issue you have a proof of concept, so we just have to understand what's going on. So this is a small snippet of code, a JavaScript code. So here, in this kind of loop, V8 tries to determine the range of the key variable. So here, the start range is from 0 to 0, because it's only 0, and the increment range is only 1. So the key range is pretty simple, it's from 0 to 99. But there is more complicated cases, like this one, where the start is plus infinity and increment is minus infinity. So here, in this case, the k range could be plus infinity or not a number. Because at the first iteration, key becomes plus infinity, but at the second iteration, we had minus infinity to plus infinity, and in JavaScript, it gives not a number. So V8 tries to determine those cases where adding or subtracting start and increment gives not a number. So the condition to determine this range is to determine if it could give not a number. It's that start and increment must be integer. So this is a check here. Both types are integer, and it includes plus infinity and minus infinity. And if both types are integer, based on the arithmetic operation which is done on the loop, it takes it's called number add or number subtract, and check if the resultant type could be not number. And if both types are not integer and or it could give not a number, the optimization is not done, and there is no optimization. But from this, we can find there is still a way to produce not a number, despite maybe none being files. So here, an example, start range here is 0. The increment range is -infinity to +infinity because at the middle of the loop, increment change. So bus types integer is true because the integer range contains the infinity negative or positive. And the number had function doesn't determine that the range could be not a number. So we have maybe none, which stays to false. So the optimization continues in this case. And when the optimization continues, V8 determines that key range could be any integer here because the increment could be positive or negative, which is what is explained here. So, but it doesn't include not a number. So we have we are able to produce a key variable that V8 thinks range is an integer, so from -infinity to +infinity, but that could be also not a number. So from this, we take our magic variable and we are doing some arithmetic operation. And at the end, we have a value here that V8 thinks it could only be 10, but it could be also not number, an internal representation of not number, which is in fact a big value. So from this magic value, we are going to create an array with this code, and while V8 tries to optimize this call with the following code. So here we see that if length it's a small integer, it's a positive number and it's less than 16, and in fact the mean value and the max value are the same, so it's a constant. It calls this function, which creates an array. From here, it takes the capacity of the array, which is a fixed value based on the length, but the length still comes from the magic value, which is very big. So we can have a very big an array with a fixed capacity of 10, with a fixed capacity of 10, but the length it's not a number, so this is a big value. So here we have the code that triggers it. So we have the function here, which we call it a very high number of time. So it gets optimized by V8, and at the end we returns an array, which is very big. So here we have our array with a fixed capacity of 10, but the length here is very, very big. So from this, we modify the trigger functions that I presented just before, and we create two arrays. So we have the big one, the big array, and we have the victim array, which is placed right after in memory. And with the big array, we are going to modify the victim array to craft two primitives that are the basic primitive for any web browser exploitation in Digit. And so the first primitive is addr_of, which given an object returns his address in memory. So here we have the victim array, in which we store the object, and from this, and with the heavy array, we are going to read the data of the victim one. And the fake object, it's given an address, return an object, so it's the opposite of the first function, which use the evil array to modify the victim one, and then we use the victim one to create an object. So from this, we can craft any object that we want. So here, basically, we craft an array buffer object, and it's allowing us to read and write arbitrary addresses. So from this, we modify the GTED code of the WebAssembly function, because the GTED WebAssembly is stored within a read, write, and executable memory area. So we just have to put our shellcode here, and then we get a a shell on the TV. So here we can see that we are not root, we are owner. Here we have the groups, which are corresponding to the privilege of the web browser. And here we have the context that Vincent are going to talk about. So we got a shell within the browser context. And from this, we're going to escalate our privilege. And Vincent is going to present.
Thank you. So from now, why we want to escalate our privileges? Because we want to search vulnerabilities in other services than the browser. So to do that, it's pretty convenient to get a root shell on the device and to be able to launch a debugger like a GDB on any binary. So when we try to exploit a vulnerability, you get everything you need to understand what is going on. So first of all, to get a privilege escalation, we need to understand what are the mitigation on the device. There's something called UOP, which is unauthorized execution prevention. And it's a protection that verifies that all the binaries that are run on the device are signed by Samsung. It's an RS signature verification, and it's enforced by the kernel. So it's performed anytime you try to execute some code. So when you perform execv system call, or when you try to load a library, or all this stuff is checked by the kernel. And then you have SMAC, which stands for Simplified Mandatory Access Control in the kernel. It's like as a Linux, you have a context, you have context transition, and every application on the device have a context. So in our case, you can see the context. It's the Tizen browser here. So next we will be looking for vulnerabilities in the kernel. So when you use open source code on your product, you have to make the source code available on your website. So you can download the Samsung kernel on the website. You can find the address in the references. So what we get is the kernel source code, many drivers as well, and some services that run on the TV that use open source software. So we will be able to read the driver source code and to understand better the Samsung custom protection added to the kernel. So after digging in the kernel source code, we quickly found this driver, which is called SDPMem. So this driver is accessible from the browser context, and it defines 3 file operations. As you can see, you can perform open, release, and mmap. So when we saw this mmap function, we saw it's pretty interesting. So then we go straight to the vulnerability description, which is in this function. And in fact, it simply allows to map any physical address on the device and to get a full read-write on all the kernel code and data section. So there isn't any check, and everything is mapped as readable and writable. And we talked before about access control, but as you can see here, the SMAC context of this driver is star. And when you look at the documentation of SMAC in the kernel documentation, you can see that any access requested of an object labeled as star is permitted. So every context on the device can access the driver. So it offers a full read-write on the kernel for any code running on the TV. So here is an arbitrary write example from our browser context. We start by opening the file descriptor on this driver, and then we use mmap2 because it's the way this driver works. And we just use a the PG offset to get an offset on the address 0, and so PG offset is the number of page multiplied by 0x1000, and then we have this 0x1000 pages that is accessible, and we just write at the desired offset a value, and we write on the kernel, and then we can close the file descriptor. So now we are able to read and write everything, but we want to think about what to rewrite, because writing to code section is always tricky. You can have some cache problems. You can rewrite code that is executed at the same time, so it can pretty easily end up with kernel panic. So we will much better prefer to rewrite some data, some code in the data section. So a good way to do this is to find a pointer that is stored in the data section and to rewrite it to first get an arbitrary call in the kernel, and then from this arbitrary call we will use a known technique to get to exec a userland binary. So first of all, how to get an arbitrary call? So in your /proc on the device, you have many files, and for each file in this /proc, you have a descriptor in the kernel that allows to read or write this file depending on the file. Here we find the proc SDP version file, which can be accessed by the browser context. And when we read the source code, you can see that there is a pointer to SDP proc show SDP version, which is executed when you read this file. So this pointer is in the data section, and you can just we can just rewrite it with our vulnerability, and we get an arbitrary call because. Okay, so now we have this arbitrary call. How to be able to execute a userland binary? We use the function orderly power off, which is in the kernel, and this function just calls the function run cmd, which is a wrapper for call user mode helper, which is a function that launch a binary in userland. This function launches the command that is stored at power of cmd, which is stored in the data section. So our plan here is just to patch the power of cmd in the data section with, in our example, BusyBox launching a netcat with a remote shell. And then use our arbitrary call to run the orderly power off. Last thing we need to do is to bypass the UOP that we talked about previously, because we need to upload our custom BusyBox to get a shell, and our BusyBox is not signed, so we need to bypass the signature check. But it was pretty easy because you have this convenient check in the kernel, which read the SUOP status variable, which is a global variable, and if you set it to 0, all signature check will return correct. So we write a 0, and the check is bypassed. And yes, before we had this pop-up on the TV. Telling us that our BusyBox process was blocked, but now it's bypassed. So if we have a quick recap of what we've done, the exploit starts by patching the UOP, then we rewrite the power of cmd string, and then we rewrite the pointer to orderly power off in the SDP proc entries. And after reading the proc SDP version file from the browser context, we can enjoy our root shell. So, yeah, we have what we wanted, and we are root. Now that we have our root shell, we were thinking about what after this vulnerabilities patch we will lose our our debug environment. So maybe it could be great to be able to decrypt the firmware, to still be able to get all the binaries on the TV and to perform some reverse engineering. So now we are going to try to decrypt the firmware. So the firmwares can be downloaded from the Samsung site. They are encrypted, as you can see on the entropy graph. And F-Secure, who has written a blog post, I think 2 years ago, has stated that the encryption algorithm is AES and that the key is decrypted in the trust zone. So you can't get the key by static reverse engineering. You need some access on the TV to try to extract this key. So this is a quick summary of how the decryption of the firmware works. The encrypted firmware decryption key is stored on the file system of the TV in the items AES passphrase encrypted.txt. And when you want to decrypt a firmware, the key is loaded in the trust zone, or more precisely in a trusted applications in the trust zone. So you load the encrypted key. You take the encrypted key from the file system, the SW standalone, which is the binary performing the update, loads it in the trusted application. Here, the key is decrypted and stored inside the secure memory of the trust zone. And then you can send your encrypted firmware, and the AES decryption is performed inside the trusted application, and the decrypted firmware is sent back to the user. So it allows to decrypt the firmware without giving any access to an attacker to the decrypted key. So, but we are going to try to bypass the way it works, and so for that, our work environment will be performing a manual update using the SW standalone binary. We plug a USB key with a valid firmware on the TV. We launch the SW standalone with a GDB server attached to the binary. And we will add many breakpoints with commands to bypass some verification and try to get the key. So yeah, here we talk about patches, but it's just breakpoint in GDB server. So first of all, we will patch this function, which is the init dub option of the Trustzone iOS engine. There is some variables that allows to debug what is going on and to write to the file system all input output of AES. So when trying to decrypt the firmware, it will help us a lot to understand what is going on. Then we have to patch the run checkers function, which because when we want to update the TV, there is a check to see if the version of the firmware we are trying to launch is already the same on the TV, and if it's the same, the update stops because you don't have to update your TV. So here we just bypass this version check, and the update goes further. And last, the third patch, in fact, so you have this Crypt engine function, and here we have two interesting parameters. We have use software Crypt engine and is Trustzone supported. So in fact, you can see that if there is the is Trustzone supported, it states passphrase will be decrypted inside Crypt engine, and in the other case, decrypting passphrase outside Crypt engine. So in fact, this patch, what it does, we take the same schematic as previously, but now when we send the encrypted key to the trusted application, the trusted application will conveniently decrypt the key and send it back to the normal world. So we can just add a last breakpoint in our GDB server to be able to print the decrypted key. So now we get to our breakpoint in GDB where we print the key, and we get this weird ASCII string, and we are like, what the fuck is this format? Because it's ASCII with \n, and we weren't expecting this kind of format because it seems pretty weird that the trusted application uses an ASCII and formatted like that. So we think that someone at Samsung just had some problem and put the ASCII version of the string in the file that is needed to decrypt the firmware instead of just putting some hexa values. So now we get this, but it's not the final AES key because it's much longer than the 16 or 50, 32 bytes we need. No, 15. 16, sorry. If we try to use this key with the software decryption argument set to 1 as seen previously, it doesn't work. So in fact, the binary doesn't work if there is no trust zone. And so we try to decrypt the key, get the X byte. We tried many tries. But we end up with writing a script in Python that tries many formats of the key and that checks the AES padding to see if our decryption is correct or not. And so we end up with this solution, which is the passphrase is the ASCII representation, and we perform an MD5 of this representation, and we use that as an AES key for IS 128 decryption. And then, so we haven't described the full file format of the update because we didn't get the time, but in fact your upgrade.msd file is contains a list of entries. You have a different IV for each file. You have some salt, and so we reverse engineered the file format, and we write these scripts that use the MD5 of the key and tries to decrypt. So when we extract the upgrade.msd encrypted file, you got all those files. So some of them are encrypted again, like this one, sequest.bin and sequestdrv.bin is the code that is loaded in the trust zone, but it's over encrypted, so we weren't able to read the trust zone code, but you get your root FS, you get a lot of stuff to perform reverse engineering later.
Thank you, Vincent. To conclude, we get a road shell on the TV, so there is no more binary signature, so we can execute what we want, a GDB server or whatever we want. We have access to the whole system, and we are in a very comfortable position for vulnerability research and debugging what's happened on the TV. We also have decrypted firmware, so we can perform static analysis on further upgrades if we lost our shell. We plan to publish the exploit and the decryption script soon, so we don't know yet when, for now. And we would like to thank our colleagues for proofreading everything, and a special thanks to David for helping us a lot. So thanks for your attention, and if you have any question, please ask.
Thank you so much for the very interesting presentation. Do we have a question in the amphitheater room? Somebody want to ask question? Yeah, can you come and you will ask question live to prove that we have physical person in the room?
Yes, there are actually a physical person in the room. Thank you very much for the presentation. I would like you to explain us how the disclosure was how was the interaction and so on.
So the disclosure started in April, I guess, or maybe before.
No, or March.
So the V8 one day was pretty quickly fixed. in the you can see it in the because you have a Git repo with the Tizen source code, and the kernel one we don't really know if it's fixed. We told Samsung that we will be doing this presentation today. They didn't say to us not to present, so we're not sure if it's patched or not. But they were it ran good with Samsung. They didn't try to stop us from doing this presentation, so it was okay.
Okay, so other question? Okay, maybe online question? So.
Il faut lire.
Okay, how many time do you take to manage these attacks? It's 1 day, 2 days, 1 month, 3 months?
I don't know, maybe for the browser exploitation, maybe 5 days, because in fact there is other vulnerabilities which are not exploitable because of compilation option, but this one was. So I don't know, maybe yes, 5 days, and for the
1 person, maybe?
yes, yeah. 1 person, and for the
for the privilege escalation part and firmware decryption, I think
maybe 5 days more.
Yeah, 5 or maybe a little more. Like let's say 15 days for the wall stuff.
Yes.
A second question online. So, does the firmware contain the security world code? Secure world code.
Yeah,
It's free.
so this is what we say before. The secure world code is here in those 2 files, but it is over encrypted, so we cannot. We weren't able to access it, to read it.
Okay, so maybe I will ask a last question. Everything you presented, is it related to the TV, or does this attack apply to another Samsung framework which use the same material or something like that? Because I never see any TV specification in your presentation, because you just plug a USB key, so it can maybe work for different devices.
Yes, maybe.
Other devices that use Tizen are watches, so I don't know if there is a browser on the watch.
I don't know.
Maybe.
Ouais.
Okay, so thanks again for the speakers.